Good morning. We're very pleased today to bring you our unit on constructing and directing the DANTE solar probe.
I'm Richard Lund, and
I'm Caleb Miller.
we both teach at St. John's High School in St. John's, Michigan. I teach and have taught before physical science, chemistry, honors chemistry, along with advanced placement chemistry. Okay.
We're very grateful for the support of our mentor Cyrus Jeans, NASA, and RTI for helping us collaborate on developing this unit. Our mentor, Cyrus Jeans, is a structural analysis specializing in dynamics and design. He's a problem solver for NASA. There's a problem, they bring it to him, he fixes it. And it was very exciting to work with him and see the variety of things that he's involved with.
Definitely.
Our unit is designed to reinforce the national standards of physical science. We're looking to bring in the ModSim experience by providing students with real-world applications of their curriculum.
And with this unit, we planned it so that way it's got 3 different lessons to it. And in those 3 different lessons, they're going to see a variety of the physical science concepts that have already been taught to them, but that now they get to see their application. A lot of times in science classes, when we have certain topics, they're corralled into chapters. This is going to get rid of those boundaries and instead show them how we can synthesize this stuff in order to solve real-world problems.
By delivering the unit in this way, we hope to bring in real-world problems using applied physics and challenging students to come up with solutions. Our goals will be to incorporate technology, the simulation programs, and spreadsheets to illustrate the relevance in STEM careers and in STEM education. Additionally, we hope to prepare students for the excitement but also the accountability that they would experience by working in a NASA simulated unit that would include 3 different and unique but very robust lessons.
So the first lesson that we have, lesson 1, and all these lessons are designed to be essentially 3 to 5 days. It depends upon how you want to modify it, how far you want to extend the various lessons. In lesson 1, with rocket probe delivery, the students are going to have a chance to design their own rockets, to test out their different ideas and actually hands-on test them with their simulations. They have a trajectory simulation where they get to kind of see what different angles would be best for their rocket delivery. The way the story goes is that we have a team of students that are hired by NASA to work with various projects, and the projects are all related to each other. The first lesson then is going to involve launching a rocket so that way it can deploy a solar probe. That's where the second lesson picks up. Lesson 2, the one that we're going to focus on today in our presentation, is the structural analysis and testing of material science and also using spreadsheet technology to show and demonstrate to the students that they can very effectively and quickly calculate and analyze data if they take advantage of such technology. There's also an orbital simulation. They have to map out what the trajectory is going to be of their solar probe so that way they can get it to measure the sun. That takes us into lesson 3. In lesson 3, the students are going to discover the focus of what that probe is actually doing, the DANTE probe. And we named it DANTE after Dante's Inferno. We figured it'd be pretty hot by the sun. It's going to be measuring the electromagnetic spectrum and taking a look kind of at the solar data that the sun gives off, similar to what the SOHO project does.
Focusing now on lesson 2, this is where we're going to be illustrating those components that we're going to highlight today. Lesson 2 is going to start by having students utilize an online resource that's incorporated by NASA where they're going to have a chance to analyze various materials for their material properties, trying to seek out the best material for their probe. After they've designed their probe, we're going to put them into the ModSim where they're going to attempt to place the probe in the best orbital path to achieve the results that will give us the data that we would like to collect. We are anticipating that this lesson will be delivered to ninth grade physical science students, students that both Rich and I have an opportunity to work with. We assume that they'll be coming to our class with a certain amount of prior knowledge that would include things from the scientific method all the way through utilizing vectors. Some of these concepts are going to be new to the students when we start this unit, but they will be concepts that we have either taught or demonstrated prior to the introduction of this particular lesson. Our objectives are to help the students realize that we want to see them show an understanding of engineering design. What goes into designing a probe? Secondly, we want them to understand that there are very real significant and insignificant limitations of models and simulations, and that they have to be able to analyze the simulations for their positives and their negatives. We also want to have the students demonstrate that they can work within the confines of a realistic budget. And this is a real-world application that we find very important, and we'll explain more about it later, but this is something that we're excited about having them learn more about. And then lastly, they're going to be accountable for collecting, organizing, and then analyzing and reporting their data. Additionally, they will gain an understanding of material science, the various physical properties of the materials that are being used. They'll have to analyze these properties and put that data into a spreadsheet where we will give them instruction on using the calculation tools so that they can determine how their probe will behave in space. They'll have to describe both mass, velocity, and gravitational relationships using qualitative analysis.
And for those of you interested in benchmarks, every single one of these is one of the national benchmarks, which in Michigan, that's what we're moving towards anyway. So we just kind of focused on those national benchmarks. Okay, so one of the things that we're going to have to introduce to them is the remote sensing. And with the introduction to remote sensing, they have to understand the definition first. Collecting information without being in physical contact with the object or the event that we're interested in. So that's essentially what probes do. And one to highlight would definitely be the messenger probe. It's currently orbiting and studying Mercury. It also contains components to it that they're going to have to consider for their fictional DANTE probe as far as the design that happened. But of course in the scientific method, if we're going to design something new, we want to research what has happened previously, what's happened before. There's a little video too that we would be showing the students, that way they can kind of get a feel for what it is a probe is doing, what the structure looks like, and what are some things that they're going to have to consider. Now the video begins with a gentleman talking about why we want to study studying Mercury. But we are going to fast forward that just a little bit to get towards the end of it and show you the actual messenger probe simulation video. This is also released by NASA, and this is where we could point out to the students, if you can see that white portion of it that just rotated out of sight, it kind of looks like a letter C right now. That's the solar radiation shield. There it is again, the upper portion. Now you'll notice that no matter which way the probe is orientated, that solar shield is always pointed towards the sun, and that's going to be the component of the DANTE probe that they have to actually design with their material science knowledge. So when we give them their mission parameters, we're going to be focusing on that solar shield material.
This is going to be a big component of the Lesson 2 unit. Students will be specifically designing this solar shield and analyzing various materials, primarily metals, but any materials that they'd like to choose to determine the best possible material on a variety of evaluation criteria. To do that, they're going to collect data from a website called MetWeb, which we have been informed from our mentor, Mr. Jeans, that this is a common resource used by NASA engineers to design their materials. They'll collect the data from MetWeb and put that into the Excel spreadsheet to analyze the materials. The MatWeb website will bring you all sorts of different physical property data when you call upon it, but we're going to have students looking at properties of density so that they can analyze the mass of the probe for liftoff to consider the cost of getting the payload into space. They're going to be considering also the specific heat so that they can be comparing that to the melting point temperature to determine if the probe, as it's orbiting the sun, as it begins to heat up, will it absorb so much heat that it would possibly melt and then obviously ultimately fail. This data is going to go right into the spreadsheet, and this is actually where they're going to do their analysis. The top screenshot here is illustrating the density calculation, and then the second spreadsheet that you see below is going to be where they're going to do their temperature analysis, comparing that amount of heat absorbed to that melting point temperature and the final temperature compared.
And to give you just a quick brief run through, they're going to take the density, and we're going to say that the NASA project has already told them what the volume is going to be. So they're going to take that density, throw it into the spreadsheet, and quickly get out what the mass of that solar radiation shield is going to be. Once they know that mass, they can then use that in the specific heat equation to take the amount of thermal energy, which we're also going to be giving to them, assuming that that's the most thermal energy that radiation shield's ever going to have at one point in time. They're going to use that in the specific heat equation to calculate out what the final temperature would give them. And then once they get all of that evaluated, they're going to have several different options that have probably worked as long as they've been looking for enough materials. But they're going to then have to take into construct the idea of, well, if these 5 materials work, which would be even better? And that, of course, is going to be the lightest one, because that's going to be cheaper for the launch cost.
Ultimately what they'd like to achieve. So this is where we get into considering how well the students did. They're going to work in groups to analyze the data, decide which of the materials would be the best viable options. We're going to give them an opportunity to work and compare their information with other groups, see if they had similar results or other results that they didn't anticipate. And then ultimately, they're going to be asked to consider the cost of launch. And in this particular unit, as well as lesson, we'll be having them analyze the expense as we go along. And of course, the lowest cost would be the winner. But this isn't really where it ends. Of course, material science goes well beyond just analyzing temperatures. There's a lot of different parameters and criteria that engineers must consider. And what are we not considering in this particular unit? These are things we want the students to think about and things that we'll discuss with them.
The model that we generated, what are the limitations in our model? And realistically, there are a few. Such as, some major components would be luster. If you have 2 materials and one's way shinier than the other, then plenty of that light that's hitting it, plenty of the radiation is going to be reflected off of it. And so that's something that a real engineer would have to consider for their radiation shield. Brittleness. If it's extremely brittle at cold temperatures, or even just brittle like during a launch, and it shatters on the launch up, then that could also be a bit of a problem for NASA. The hardness factor. This needs to be fastened to the probe in some form. So if you can't drill into it or bore into the holes of it, then how are you going to fasten it there? And then one specifically brought up to us by our mentor is probably the most important one, the coefficient of thermal expansion. In other words, how large is this going to get? How much is it going to expand when it gets close to the sun and is receiving that heat? If it can get really expansive, then that's going to cause a lot of strain on the fasteners. That's going to cause it to sometimes yield, warp, buckle, and it could even cause it to break. So what we want to drive home to the students then is that what we've given them is like a taste of what has to be considered by an engineer. Realistically, they have to consider all of it.
And so what do real engineers have to consider? Well, they have to consider everything. All those things that we just discussed, and more importantly, will they be able to keep it within budget?
Okay, so that's kind of the first step to this lesson. We've got a second step now. They've got their probe. They need to decide where they want the trajectory to be. and they have to understand that not all orbits are great orbits. We're used to a nice, healthy, good orbit here on Earth, but when we're actually putting some new satellites into space or probes into the vicinity, we have to take into consideration what is that trajectory going to be, position and velocity. So now it's like it's switching gears between material science and actual trajectory, but that's what we want them to see, the fact that it's not just one small area that somebody might work in. They might have to expand into a bunch of different areas and synthesize all together what they've been learning about in our courses. So to introduce them to this idea of not all orbits are created equal, we're going to show them this video. This is of the Iridium 33 and the Cosmos 2251 collision. What you're seeing now here on the screen, here's the Iridium satellites, how they're mapped out in orbit. There's Iridium 33, and it's on a trajectory course. You can see it from the blue line, and it's on a collision course with Cosmos 2251. This is also similar to the simulation program that the students are going to be using, so it kind of familiarizes them with it. You can see after the collision, it's also showing the space debris that is a result of it, and it's also showing how it maintains that force. You could also bring up here, objects in motion tend to stay in motion. As far as after the collision, the debris seemed to be going just about along the same trajectory as what was originally there. This is a major concern with the space debris because not only could that cause complications, it's all amongst a much larger network of satellites that are orbiting the low Earth orbit. And there's a view with the green portions of the other space objects that are already in orbit. You can see it's like a beehive of activity that we have going on with these different satellites, and all their trajectories would have to be taken into consideration as best scientists could for purposes of launching new satellites or launching space probes. So we want them to be looking at this idea of trajectory, and that's kind of like a nice way to introduce it to them. But then we'll have them load up their PhET ModSim program, My Solar System, and with this program, they're going to get a chance to play around and determine what the trajectory is. We want to take you just through a little walkthrough on it as far as how this program's used. So we're going to load up our simulation system here. This is the simplest one that you're seeing on the screen. You've got two bodies. Essentially, you could call it the sun and some particular planet. You have an initial velocity as represented by the arrow. It shows you the direction, and then how large the arrow is showing you the magnitude. And if we start this, we're going to see the effects of gravitation on an orbiting body. And it's allowed to run for a while. You can also alter the speed. The slower you make this simulation, the more accurate the calculation is going to be for the orbital paths that you have. The faster it goes, the less accurate. When you're dealing with a system like this, the accuracy of the path, the trajectory, isn't going to be altered too much. But when we get into something a little bit more complex, it definitely can. You can also stop the simulation, restart it again if you want to, and if you stop it and hit reset, then you can see the original place where you were before. Taking a look at the bottom portion of the simulation, you've got a data table that also shows you the mass of each body, the X and Y coordinate position relative on this grid, and you also have the velocity X and Y vector components. We're going to switch it over here to 4 bodies because this is going to be kind of the branching point for our beginning simulation with the students. We do need to change body 4, the green sphere, which we're going to have represent Mercury. We're going to change that value to a 2, and then that's where we're kind of leaving it. Now this probe here, the blue sphere, this is going to represent our DANTE probe. And as you can see, you can modify which initial position it starts in by just clicking on it and dragging it over. You can also have the degree of freedom of modifying the velocity. You can either lengthen it or change direction. So this gives them some degrees of freedom to use with it. Now, they're going to have to choose the initial position and velocity of this probe, and they have a few parameters that they're going to have to look at. The mission components, then, for their DANTE probe deployment, they must start between the Sun and Venus. We're going to have the purple sphere represent Venus, the Sun, of course, represented by the large yellow one. It can be anywhere on the y-axis, but they must be restricted between the Sun and Venus on the x-axis. We also are telling them that it must orbit the Sun 20 times to collect enough data that the DANTE probe needs to for the mission. And they also have a time constraint. The power cells on their probe is going to be up in 36 months, so they must have the 20th orbit occurring within 36 months. We didn't put it on the list, but hopefully it goes without saying that certainly the probe also cannot crash into a planet or the Sun prior to recording the 20 orbits of data. So let's give you a look at what they might be doing with that. We're going to load up the sim again. And what the students are first going to probably want to do is they're just going to have fun with it. They're going to do some trial and error. So maybe we start out here and see if this is going to be a good trajectory. And we run the simulation, and obviously that was a little bit of a failure there. So that would be some bad data. That's not a simulation they're going to want to catch. So they're going to want to maybe try something brand new. And they're going to do probably a lot of just trial and error to see what works and what doesn't at first. They're going to explore it. But we're also going to encourage that they try to use a bit of the scientific method. If they do wind up with some sort of bad data, then what we're going to want them to do is maybe change just one variable at a time and try to reinforce that idea of scientific method and experimentation. You can reset it to back where you were, and now instead of changing the position and the velocity, maybe I just want to tweak it a little bit and see if I get a little bit of a better result. And then I can run the simulation again. As they are going through these simulations, when they find one that is either close to or has achieved success of the mission, then they're definitely going to want to jot that down in a data sheet we'll provide them and record it. What they can do is, let's assume if this were to continue being a good trajectory course, they can stop it, reset it, and take a look at the data table near the bottom and record those values in their data sheets. In their data sheets, in their data tables, they have already the parameters for Sun, Venus, and Mercury established for them, because they're not altering any of those. And then they would record the XY positions and the XY velocities. So let's assume then we get a close to correct trajectory course. We're going to have an official test. So they're going to have to rely on their simulation. We're going to come by and observe that they actually did get a good trajectory. So they're going to want to have those values recorded. We come by and say, okay, launch your probe, let's see how you did. They start it out, and if they can get the 20 orbits before the time, which has no units here, but we're going to assume represents months, if they can get it before the 36 months, then they would be in good shape. This one looks like it could go to completion, but there are sometimes small little variables that might cause it to spin out of there, perhaps a gravitational effect due to the Mercury planet, the green one that's orbiting it nearby. Now, in addition to that, there's some ways that we can show them with this simulation some of the other ideas of gravitational effects, including a really interesting one, the slingshot effect. If you go back to the simulation program, we have in the upper right hand corner presets, including sun, planet, moon. They've got binary stars, and we also have the slingshot preset. And with this one we can see the slingshot effect. We've got the blue body, which is about to line up with the purple body. And now it's getting pulled in by the purple body's gravitational force, and it has been given that little kick out of the solar system. We can talk then about the proximity and how that affects the gravitational force causing the slingshot effect. They also have a double slingshot, which is another interesting one to see. With the double slingshot effect, now the green body is getting pulled by the purple, kicked out a little bit, and then it gets another boost in the arm from the blue sphere, getting it to also leave the solar system. Now, for those of you who know your history pretty well, in '77 we had a nice example of the slingshot effect. We had the Voyager probes 1 and 2, which took advantage of a very rare positioning of the planets. They weren't lined up in a duck row, but they were aligned in such a way that they could achieve this. We have a quick video on that that would also be showing the students after they've utilized this simulation program for a while. So this is showing you full screen now the Voyager trajectories. You can see there's our solar system, say hello to the third one from the sun. That's us. And as you watch it rotate, as it zooms in, we're going to see the trajectories of both Voyager 1 and Voyager 2 leaving Earth, and they're going to take advantage of the slingshot effect from the planets, the outer planets. There goes the 2. You can see as they approach Jupiter, they were studying Jupiter and then also got a nice kick from the slingshot effect from them. As it approached Saturn, Voyager 1 split off from Voyager 2. Voyager 2 continued on and was able to wave hello to Uranus coming up, which eventually gave it another slingshot effect over to Neptune. There's Uranus. And here comes Neptune. Now, the planets must obviously cooperate for this. And what's kind of interesting, a little factoid, is that the last time the planets had aligned in this way, Thomas Jefferson was president of the country. So it's kind of a nice little tie-in there, and a little bit cross-curricular as well. Now the last portion of this for assessing, we have a nice project geared up for them.
And I would like to mention that one of the things that we were able to do on our visit here to NASA was to learn more about the history of the rockets, the probes, the events that have taken place, and it's more meaningful for us to take that back to the classroom now, share that with the students, and it's something they're excited to tell them about Voyager and SOHO and some of the other programs that NASA's working on. And so to bring that excitement out in them, what we'd like to do is challenge them to design their own probe. They're going to start by deciding, first of all, which object in space would they like to measure. We're not going to limit it to any particular object. At that point, what do they want to measure? What is it that they're going to be measuring, and what type of equipment, and how are they going to fund the development of this probe? Another part of our budget component that will be the ultimate assessment for this 3-lesson unit. The devices that they're going to have to include on the probe, the materials that can go back to the mat web and consider some of the various physical properties, the type of power supply. Are they going to be taking advantage of solar panels, or are they going to be using some sort of nuclear energy to power their probe? And then, of course, how can they minimize cost? What are ways that they can work to come in under budget or meet their budget requirements with the idea that this is what's going to ultimately determine getting to the launch pad? Students are going to be assessed then on the material spreadsheet that they developed, the original spreadsheet that was designed for the DANTE probe. They're going to be tested on the orbit simulation data sheet, the one that they will be compiling while they're running the simulation. They will also be tested on the official probe test when we come around. And then lastly, the student design probe report will be the last component of the student assessment for this particular unit.
They also have the team budget, where they'll receive different deductions for things like heavy materials, if they crash a probe, or anytime they have to do an expert consultation, which means they have to ask the teacher the question. We don't want to discourage them from asking questions, but we do want to encourage them to try to find the answers out first before consulting us. The next steps, the places where we're going to take this is immediately into our physical science curriculum. We work with a Science Olympiad team where we are going to produce for them different challenges. We're also going to modify it, advance it a little bit more for our advanced chemistry and physics classes at our school. We indeed plan on doing an entire school district in-service to disseminate this out to the rest of our school district. I have a meeting with MSU AP Chemistry professors for professional development every month, and so Caleb and I are going to present to them. We're also going to take this to the Michigan Earth Science Teachers Association conferences in October 7th, and then a much larger, broader group, roughly 2,500 teachers attending, is the Michigan Science Teachers Association conference, which is on March 9th of next year. There's definitely also a press release in the works, and so we'll be showing the whole community this. We did want to we wanted to leave you with just one last visual of that simulation. It was one that we kind of experimented with on our own, and finding that the pointing and dragging of those bodies is kind of an interesting way to try out new things, but we can also do it by just trying to use some mathematics and find that if we have symmetrical patterns with the numbers, if you take a look at the data table down here, we use some symmetry with our position and vectors. We're attempting to show a double star pattern. And you can get some creative things out of this. Certainly when your students are finished with this simulation in class, they might just accidentally load it up at home and still want to play around with it. You're also going to see something occur nicely at right around time 60. This is symmetrical, but there are limitations also to this model. They cannot calculate perfectly the symmetry that the numbers represent. There is some margin of error due to the rounding. And so the orbits do start to decay. And this occurs in about 5, 4, 3, 2, 1. And now they're a little bit loose and wild, and the stars that had that nice symmetry, well, meeting adjourned. We'd like to leave you one last thought, and this is from a personal hero of ours, Carl Sagan. Imagination will often carry us to worlds that never were, but without it, we go nowhere. And if we aren't inspiring the students with the exciting facilitation of what we're teaching them, then we're not doing our job. So we want to definitely develop an entire unit that really breaks down those barriers of this is chapter 10, this is chapter 11, and this is chapter 12, and show them instead that all of this stuff comes together in order to have some real exciting missions and solutions to problems.
And we're grateful to NASA, the RTI, and all of the mentors that collaborated with us over the last 2 weeks, that we can bring this back to our classroom and share this excitement with our students. Thank you very much.
Thank you.